So the next thing we are going to read is Clausius theorem or Clausius inequality statement, okay, or Clausius inequality uh, theorem. Okay, in Clausius inequality theorem, what does he say? He says that the cyclic integration of dq by t is going to be less than equals to 0. Now this equation gives us the criteria for possibility of a cycle. Okay, if there is a cycle, if there are some conditions are given to you that this much amount of heat I am going to give to the system and this much amount of work I am going to get. Okay, so in such cases you need to apply the first law of thermodynamics and the second law of thermodynamics. Okay, after applying both these things, if there is a possibility is shown that okay, this thing is possible according to the second law of thermodynamics or the first law of thermodynamics, then only you can apply the proposed theorem, okay, or the proposed project which you are going to establish. Okay, that means you are going to give some heat and you are going to take out some work. So this is going to be fulfilled by this equation combined with the first law of thermodynamics. Now first law of thermodynamics you can easily understand. If the work you are going to take out is less than the heat given, then easily you can say that okay, this is the first law of thermodynamics. The first law of thermodynamics is going to be there. Okay, but after applying the second law of equation, then only you can understand whether this is actually possible or not. Okay, this is the inequality criteria. Okay, they say that cyclic integration of dq by dt is less than equal to 0. Okay, that means what? In some cases it is going to be less than, and in some cases it is going to be equal to. Okay, now if the cyclic integration is going to be equal to 0, then you must know that this thing is only possible for reversible cycle. Okay, and if the cyclic integration of dq by t is going to be less than 0, then you must know that the system or the cycle it has been proposed for is going to be irreversible. Okay, and if you see that dq by dt is greater than equals to 0, this is not possible. Okay, this is not possible. So this thing you need to know about the Clausius inequality statement. Okay. Okay. The next topic we are going to study is reversible heat engine. Okay. Now what is reversible heat engine? Reversible heat engine is nothing but it is a device which takes the heat from a higher temperature reservoir. Okay. Or higher temperature thermal reservoir. It takes some heat from there and it converts some of the heat into work. Okay, it's just because the complete heat is impossible to convert into complete work. That is the reason some of the work is taking out. Okay, we are taking out some of the work which has been converted from this heat, and the remaining heat which has not been converted from this low grade energy to high grade energy, that has been deposited to our thermal reservoir with lower temperature. Okay, now let us apply the first law. Okay, what is going to be the first law? Now according to the first law, we know that for a cycle, okay, summation of q is equals to summation of w. Okay, now this is the cycle. Okay, here a cycle is continuously running. Okay, so from this cycle, what is the heat interaction? The heat interaction is going to be QH minus QL. Okay, and the work interaction is going to be W. Okay, so from the first law we know this one. Okay, now one thing we have missed here is that whatever the Clausius equation we have written, okay, the Clausius inequation we have written that cyclic integration of dq by t is less than equals to 0. Okay, now this inequation is known as the mathematical form of second law of thermodynamics. Okay, this thing we need to remember. This thing is known as mathematical formulation of second law of thermodynamics. Okay, so since we have said this is reversible, so in case of reversible, the second law is going to be summation of dq by dt is going to be 0. Okay, summation of or the cyclic integration of dq by t is going to be 0 since it is reversible, and it would have been less than if reversible was not mentioned here. Okay, so this is going to be the second law. Now in this cycle, what is the dq by t? We can write from this cycle that QH by TL. Okay, from temperature TH, QH is coming. Okay, so the change in or the heat interaction is going to be, the heat interaction for this one is going to be QH by, sorry, TH, QH by TH. Okay, and since it is cyclic integration, that's why there will be the summation of all the dq by t. Okay, now I have written minus because here QL is getting rejected from the cycle. Okay, from the cycle QL is getting rejected. So before that there will be minus. And what is the amount of heat that is getting rejected? That is QL. And at what temperature? The temperature would be TL. Okay, this is going to be the second law equation. Okay, so from this equation we can easily write that QH divided by QL is going to be TH divided by TL. Okay, we can easily write it from here. Okay, now let us find the efficiency of the reversible heat engine. What is going to be the efficiency? Now if you write down the efficiency here, what is going to be the efficiency? Efficiency is nothing but W net, or whatever the work that is coming out, net work that is coming out divided by Q in. Okay, now W we have found out what? We have found out W equals to QH minus QL divided by Q in. That is Q in means what? Whatever the heat you are going to give. So Q in is going to be your QH, because this is the amount of heat you are going to give to the system so that it can convert that heat to work. So Q in is going to be QH. Okay, now if you can write it like this: 1 minus QL by QH. Okay, so this is going to be the efficiency formula. This is going to be the efficiency formula. Now we can see that QH by QL is going to be TH by TL. So that means that QL by QH is going to be TL by TH. So we can write it as 1 minus TL by TH. Okay, efficiency, thermal efficiency. Okay, so thermal efficiency is going to be equal to 1 minus TL by TH. Okay, now another thing you need to remember here is, this is the equation. Whatever the equation is here, this thing can be applicable for reversible as well as irreversible. Okay, as well as irreversible. For this equation of thermal efficiency must be same for reversible as well as irreversible. But this equation, 1 minus TL by TH, okay, 1 minus lower temperature by higher temperature, this thing is only for reversible. Why only for reversible? Just because this is reversible, we have taken this equals to 0. Okay, this equals to, otherwise if it was irreversible, then we would have written it is less than 0. But since it is reversible, then that's the reason why we have taken dq, in cycle integration of dq by t is going to be 0 or equal to 0. Now from this equation we have derived that this is the case. But here, up to here it is normal. Okay, in any of the heat means, whether it is reversible or irreversible, you find out the efficiency like this only. Now just because this is reversible, that is the reason why QH by QL is going to be TH by TL. Okay, just because it is reversible. So applying that or defining that the system is reversible, only if it is defined that the system is reversible, then only we can take QL by QH as TL by QH. Okay, so that is the reason this is applicable for reversible or irreversible, but this has to be only reversible. Okay, this has to be only reversible. Okay, reversible refrigeration. Okay, so in refrigeration what happens? Refrigeration is nothing but the layout is complete opposite to the heat engine. Okay, now what happens, as we have told earlier, that in refrigeration what happens, we need to make the temperature of certain space lower than the atmospheric temperature, and for that we need to maintain the temperature also. Okay, and to maintain the temperature we are operating this on a cycle. Okay, that is if we are operating this on a cycle, then only we can maintain the temperature or lower temperature than atmospheric temperature. Okay, now what happens, as we have told earlier, to take heat always flows from higher temperature to lower temperature. That's why in previous case we are getting work output. Okay, now we are opposing the law of nature. Okay, we are opposing the spontaneous processes of nature. In spontaneous process, what happens? Heat always flows from higher temperature to lower temperature. Now we are willing to take heat from lower temperature to higher temperature, and for this reason we are giving some work input. Okay, now after giving work, what happens in refrigeration? From temperature TL or the lower temperature reservoir, heat is going out, that is QL. L is supposed to be lower. Okay, L is and it is supposed to be higher. That means whatever the heat it is taking from lower temperature reservoir, that is going to be QL, and whatever after giving heat, these two will combine and give the heat QH to TH. Okay, or the thermal reservoir is higher temperature, it will pass on the heat called QE. Now similarly we are going to apply first law. In first law, what happens? We know that summation of heat interaction is going to be equal to summation of work interaction. If these are going to be same, then this is the system. Okay, the red dotted line is going to determine the system. Now in this system, heat is going in, QL is going in. Now heat input to the system is positive, so that is the reason we are writing QL. Okay, now this is the QH which is going out of the system. Okay, so heat going out of the system we are taking as negative. Okay, in the sign convention we have read. Now we need to do the work interaction. Now work interaction in the or work done on the system is always considered to be negative. Okay, that is minus W. So from here we can write that W is equals to QH minus QL. Okay, QH minus QL we can write. Okay, similarly for reversible refrigeration, if we apply the Clausius equation, since it is reversible, it will be equation only. So this is dQ by T is going to be equal to 0. Okay, so here what happens? Now this is the heat which is going to be into the system, so this is going to be positive. Since this is going to be positive, so we can write it as QL by TL, and similarly this is going to be negative. Okay, since QH is going out, so this will be QH by T. Okay, this is going to be equal to 0. So from here you can easily write that QL by QH. Again similarly we can write that QL by QH is going to be equal to TL by TH. Okay, now in refrigeration there is not efficiency. Okay, there comes coefficient of performance. Okay, now coefficient of performance for refrigerator, what would be the refrigeration? Now they will take the input energy below. Okay, so like the previous one, we have said that whatever the Q you are giving, okay, now you give energy to a system, whether it is reversible or irreversible, you need to give energy to the system. In some places, suppose like in heat engine, you give the energy in terms of heat. In reversible refrigeration, we give the energy in terms of work. Okay, work is also an energy, heat is also an energy. Now in reversible refrigeration, what happens? We give the energy in respect to work. Now whatever you have given will come below. Okay, that is W. Okay, this is going to come below. Okay, now whatever the output we are getting, okay, to get the coefficient of performance, we need to write the desired effect. Okay, desired effect, or whatever the heat we need and whatever the heat we are getting out. So here this would be the desired effect. Okay, for refrigeration we need to take this, we desire to take this amount of heat from the space so that it can maintain a temperature lower than atmospheric temperature. So for refrigeration, this is going to be our desired effect. So here you must write this is QL. Okay, here you must write this is QL. Now from the first law, we have seen that QL is what? QL is nothing but QH minus QL, and it would be QL. Okay, now this is going to be the formula for coefficient of performance of a refrigerator. Okay, this is going to be the formula. Okay, now let us divide all these things by QL. Okay, all the terms in numerator and denominator we divide by QL. Okay, now what will we get? Here we will get 1 because we are dividing by QL. Okay, we are dividing by QL, that's why we are going to get, or let us divide by QH. Okay, so QL by QH is there, and here you are going to get this. Okay, QL by QH. Okay, this is the term you are going to get. Okay, now for reversible, what we have seen that this is the condition for reversible, similar like previous one, that is heating here. Okay, now in similar case for reversible, QL by QH is going to be equal to TL by TH. Okay, so the same thing we can write it as TL by TH divided by 1 minus TL by TH. Okay, now if you do, or if you simplify this expression, you will get the similar expressions like TL divided by TH minus TL. Okay, this would be the COP of refrigeration. Okay, now in similar cases, or like the previous one, we must say that this formula and this formula. Okay, now this formula is going to be equal for either reversible or irreversible. Okay, applicable. Okay, this thing is going to be applicable for reversible or irreversible. If the heat amounts are given, QL QH is given, either it is positive, either it is reversible or irreversible, you can use for both the cases this formula. But this formula will be applicable if it is mentioned that the system is reversible. Like the previous cases only, this has to be mentioned that this is reversible, then only you can take the coefficient of refrigeration, and the temperatures are only given, higher temperature and lower temperature, then only you can take that this is going to be reversible. Okay, now what happens if you consider that this is the reversible refrigeration, and now let us consider that this is going to be a reversible heat pump. Okay, now in heat pump what happens? Heat pump, the mechanism or the layout is going to be completely same. Okay, it will be going to be completely same. But in case of refrigeration, what happens? We need to maintain a temperature lower than the atmospheric temperature. Okay, so suppose this is atmospheric temperature and this is the space we need to maintain at lower temperature than atmospheric temperature. In case of refrigeration, I am saying. Okay, so this was maintained at atmospheric temperature, or suppose this reservoir is temperature only, and this is the space where we need to maintain. So what we did, we have taken out some heat from the space at lower temperature and we have given to the atmosphere. Now in case of heat pump, what happens? The mechanism is completely same, but now this is going to be our atmosphere, and this is going to be a reservoir which is higher than the atmospheric temperature. In heat pump, we need to maintain a temperature higher than the atmospheric temperature, and we need to maintain that temperature. Okay, in heat pump what happens? The mechanism is going to be completely same. Now this is going to be our atmospheric temperature, so we'll take out the heat from atmospheric temperature or the reservoir, thermal reservoir, okay, at lower temperature, and we'll give the heat to a space where we need to maintain a temperature higher than the atmospheric temperature. Now we need to maintain that heat, we need to give continuous heat, so that's why we are operating it on cycle. Okay, now what happens? This heat is continuously be deposited in this reservoir and will maintain that space in higher than atmospheric temperature. Okay, now for the heat pump, everything up to here it is going to be same. Up to here it is going to be same. The thing comes when we need to find the COP of heat pump. Okay, now in COP of heat pump what happens? COP of heat pump, we need to take the desired effect, okay, here, and whatever the work you are giving or whatever the energy you are giving, it will come at the bottom. Okay, now similarly this is the work input, similarly this is the work input. So in the numerator what will happen? We need to give the desired effect. Okay, so how much energy it is taking out from the atmosphere, it is not our concern for heat pump. it was our concern for refrigeration. So how much amount of heat we need to take to maintain the temperature. Now this is our concern, how much energy we need to give to the space, so that how much heat we need to give to the space, so that this temperature is maintained at higher temperature. Now our concern is this, our desired effect is QH, this much amount of heat we need to give to the space, okay, or the space where we need to maintain a temperature higher than atmospheric temperature. So this will become, the desired effect will become QH, okay. Similarly here it will become QH. Now if you do it like this, similarly you will get the final expression as TH, okay. This thing may not be same, this thing may not be same, but for this you can say that this is going to be the coefficient of HP. This is also going to be the coefficient of performance for heat pump. Okay, this is going to be the coefficient of performance for heat pump. Okay. Now let us rub this. Now you will see that if you subtract the coefficient of performance for heat pump, okay, if you subtract the coefficient of performance for refrigeration from the coefficient of performance of refrigerator, what will happen? You will get the value equals to 1. Okay, you will get the value that is equal to 1. Okay, we get the value equal to 1. So from this we can write that coefficient of performance for HP is going to be equal to 1 plus coefficient of performance for R or refrigerator. Okay, this is going to be, if the same, that means if the same temperature difference is given, okay, now you need to convert that heat pump into refrigeration, then you can convert it like this. Okay, you can find the COP of HP. Okay, suppose they have given a question like this, this is our refrigeration. Now we need to convert this as, our heat pump. Okay, it was a refrigerator, we need to convert it as heat pump. So you need to find the coefficient of performance for refrigerator, then add 1 to it, then you will find the coefficient of performance for heat pump while it is converted from our refrigerator. Okay, while it is converted from our refrigerator, then only we will get this. Okay, so this is our concept of reversible heat pump and reversible refrigeration. Okay. Okay, so now we are going to look at coupled engine. Okay, coupled engine means what? Two heat engines are coupled together. Okay, so previously what happened? This heat used to come out from higher thermal reservoir or higher temperature thermal reservoir, and it used to give the heat to the lower temperature thermal reservoir, and by that heat we are going to get some work. Okay, now what happens? This heat, whichever it is coming out, now that heat is again going to be the input for another heat engine, that is heat engine 2. Okay, that means whatever the heat this heat engine was rejecting, we are using that heat to convert work from another heat engine. Now that heat, whatever it is going to give us, is going to give that heat to this thermal reservoir T. Now this is going to act as our, for this heat engine, this is going to act as our sink. Okay, our heat used to get deposited in this reservoir. Now for this reservoir, the same sink which was used for 1, that is the heat engine 1, now we are using that same reservoir as the source of heat engine 2. Okay, now we are taking out heat from this reservoir and we are getting some work. Okay, so work coming out from heat engine 1 is going to be W1, heat coming out, work coming out from heat engine 2 is going to be W2. Now as we have learned from the earlier first law, so from here what is going to be the first law? W1 is going to be QH minus Q. Okay, since here is no QL, that is Q. And W2, what is going to be the W2? W2 is going to be Q minus QL. Okay, this is going to be, now as we have derived the efficiencies, for heat engine earlier. Okay, so from that what we have seen that efficiency efficiency of the first heat engine, that is efficient eta 1. Eta 1 is going to be our lower temperature by higher temperature. Okay. Now if this engine is reversible, then what was the condition for reversible? It was 1 minus T by Th. Okay, this is only when this is reversible. Now eta 2 is what? This is the efficiency of the heat engine 2, which has been coupled to heat engine 1. So from here, what is going to be the efficiency? 1 minus, here the lower temperature is QL. Okay, here the lower temperature is QL. Okay, divided by what is the higher temperature here? The higher temperature here is Q. Okay, now if this is reversible, again we can write 1 minus TL by T. Okay, these are the efficiencies of this coupled heat engine. Okay, the heat engine 1 and heat engine 2. Now from this we need to express 2-3 conditions. Okay, 2-3 cases, and finally we will derive the overall efficiency of this coupled engine. Okay, the overall efficiency of this coupled engine. Okay, so for that let us take case 1. Okay, case 1, let us say that this W1 is going to be equal to W2. Okay, we are finding this case 1 so that we can find the relation between TH, T and TL. Okay, that means to get the W1 and W2, what should be the temperature of the intermediate reservoir which we are going to need to make the couple between these two. So to find this condition, we are going to take case 1. So for case 1, let us take, we need to take same work output. Okay, so that means if same work output is there, that means we can write Q1, so W1 is equal to W2. Okay, from here W1 is going to be equal to W2. So W1 is going to be QH minus Q, and this is going to be Q minus QH. So QL. Q minus QL. Okay. So from here we can write QH plus QL is going to be 2Q. Okay. This is going to be 2Q. Okay. Now let us divide by Q. All these cases we are dividing this by Q. So QH by Q is equal to plus QL by Q is going to give us 2. Okay, this is going to give us 2. Now if you expand this, now from this equation, or if the system is reversible, okay, or if the heat engine is reversible, what we have taken, we have seen that Q by QH is going to be T by TH if the system is reversible. So QH by Q must be equal to TH by T. Okay, if this is reversible, Q by QH becomes T by TH. So QH by H will become TH by T. Okay, plus QL by Q becomes TL by T. Okay, TL by T. Okay, this is going to be equal to 2. Now if you take the LCM, what happens? T and TH plus TL is equal to 2. Now from this, if you need to find T, what will you get? You will get TH plus TL divided by 2. Okay, that means what? T must be the arithmetic mean of the highermost thermal reservoir and lowermost thermal reservoir. Okay, that means to get the same work output, that is to make the same work output, what we need that this must be, okay, to get the same work output from a coupled engine, so from engine 1 and engine 2, we need to take this temperature as arithmetic mean of. We are going to solve some of the questions from second law. Okay, so this is the question which is given in the figure. E is the heat engine with efficiency. This is the figure they have given. In the figure, E is the heat engine with efficiency 0.4. That means this is the heat engine, and this heat engine is having an efficiency of 0.4. R is a refrigerator. This one is a refrigerator. Okay. Now they have given an equation. Q2 plus Q4 is going to be 3Q1. Okay. Q2 plus Q4 is going to be 3 into Q1. Okay. Find the COP of the refrigerator. Now we have to find the COP of the refrigerator. First of all, we need to see that what they have given. They have given efficiency 0.4. They have given this equation. Okay. So if this is the engine, first of all, let us see what is the efficiency. Efficiency is nothing but for a heat engine, which we have found out is W by work done by Q1. Okay, that means whatever work you are going to get and whatever heat you are going to give as input. So this is the W, and we all know W is nothing but Q1 minus Q2. Q1 minus Q2. Because according to the first law of thermodynamics, if this is a system, then what? Then your work interaction must be equal to the net heat transfer. Okay, net heat interaction is going to be equal to the net work transfer. So that's why W is going to be equal to Q1 minus Q2. Q1 is positive since Q1 is going into the system. Q2 is negative because Q2 is leaving the system. Okay, so from here you can write Q1 minus Q2 divided by Q1, and efficiency they have given as 0.4. So this is going to be 0.4. Okay, so if you simplify this equation, what you are going to get? You are going to get Q2 is going to give you 0.6 of Q1. Okay, because Q1 is going to get multiplied here, so it will be 0.4 Q1, and there is 1 Q1 left here. Okay, this will go this side. Okay, so this one is positive. If it goes to this side, then it will be negative. So positive 0.4 Q1 minus 1 Q1. Okay, so the subtraction will give you 0.6 Q1. Okay, so this side there will be negative term, this side there will be negative term. So negative if you cancel out, then this is the final expression you will get. That is Q2 is going to be equal to 0.6 into Q1. What we have found out here? We have found out a relation between Q2 and Q1. Okay. Again, they have given us a relation. This one. They have given us a relation Q2 plus Q4 is going to be equal to 3 into Q1. Okay. Now, in this heat engine, this one is having a higher temperature. This one is having a higher temperature. So, Q1 heat engine always takes heat from higher temperature and gives to a lower temperature. Okay, so this is the heat engine. But in refrigeration, this is lower temperature and this is higher temperature. Why? Because the direction they have given is this way. And what is the work of a refrigeration? What is the working principle of a refrigeration? The work of a refrigeration is to create a temperature lower than the atmospheric temperature. Okay, create a temperature and maintain the temperature. That means you need to take out heat from that lower temperature to maintain that in lower temperature. Okay, so in this case, this is the lower temperature. For heat engine, this is the higher temperature. Okay, in refrigeration, what we have seen, that previously we have seen that when you give work, we have taken lower temperature here and higher temperature one. That's why we have given our direction this way. But in this case, they have given our direction this way, so we have to assume that this one is lower temperature and this one is higher temperature. Okay, so we have found out the relation between Q2 and Q1. Again, from this one, Q2 is given as 0.6 Q1. 0.6 Q1 plus Q4 is 3 into Q1. From here, you are going to get a relation between Q4 and Q1. So from here, you can easily write Q4 is going to, this is going to be get subtracted from this one. So the remaining thing which you are getting will be 2.4 Q1. Okay. So this is the relation between Q1 and Q4 we are going to get. Now they have told us to find the COP. What is going to be the COP? COP is what? COP is nothing but whatever the required effect, okay, desired effect. So for temperature, whatever heat is taking it, whatever heat it has been taking out from the lower temperature, okay, this is a reservoir with lower temperature. So in refrigeration, what we have said that whatever the heat it is taking out from the lower temperature to maintain that temperature in this temperature only, so that heat is going to be in numerator, sorry Q3, that heat would be in numerator, and in denominator is whatever the input energy you are giving. The input energy you are giving is W. Okay, W, that is work, this work you are going to give. So what is W here? W is Q1 minus Q2. Q1 minus Q2. Okay. Now we have found out relation between Q4 and Q1, Q2 and Q1. We do not know anything about Q3. Okay, we do not know anything about Q3, but we know that for this refrigeration also first law is applicable. That means total heat interaction is going to be equal to total work interaction. Okay, so that means what? That means what? This thing and this thing will combine to form this one, Q3 and W. Okay, so we can write here that Q3 is going to be equal to Q4 minus W, or else for refrigeration you can write total work interaction is what? Q1 minus Q2 or W, Q1 minus Q2 or W. Okay, this is the work interaction, but this would be negative. Okay, or you can write it as minus W. Minus W equal to what? Total heat interaction. Total heat interaction is Q3 minus Q4. Okay, so if you bring Q4 this side, then what will happen? Q3 is going to be your Q4 minus W. Q3 is going to be your Q4 minus W. And again W is what? W is nothing but Q1 minus Q2. So your Q3 is going to be Q4 minus Q1 minus Q2. Okay, this is going to be your Q3. Q3 equals to Q4 minus Q1 minus Q2. Okay, so we are putting the value of Q3 here. So what will be the value? Q4 minus, so it will be minus Q1, minus and minus, it is going to be plus, so plus Q2. Okay, and in the denominator it will be Q1 minus Q2. Okay, now what we need to do, we need to combine all these Q2 and Q4 in terms of Q1, so that finally Q1 gets cancelled out and we get a value which could be our COP. Okay, so Q4 is what? Q4 is nothing but our 2.4 Q1. So we can write 2.4 Q1. Okay, minus Q1 is there in terms of Q1 only, plus Q2 is what? Q2 is nothing but 0.6 of Q1. Q2 is 0.6 of Q1. So it is 0.6 of Q1. And in the denominator, Q1 minus Q2 is what? Q1 minus 0.6 of Q1, because Q2 is equal to 0.6 of Q1. Okay, so if you calculate this in the denominator, it will be 0.4 Q1. Okay, in the denominator it will be 0.4 Q1, and in the numerator what is it is going to be? 2.4 plus 0.6 is going to give you 3 Q1 minus 1 Q1. That is 3 minus 1, it is going to give you 2 Q1. Okay, so Q1 and Q1 is going to get cancelled. So the final answer what you are getting is 5. Okay, so this is going to be the COP of the refrigerator. Okay, so this is the condition, efficiency they have given, one equation they have given. Now if you solve this in this way, you can easily find what is the, if efficiency is given, you can easily find what is the coefficient of performance or COP of a refrigeration in this way. Okay, so now we are going to see another question. So they have given a question like this: efficiency of a Carnot cycle is given as 0.75. Efficiency of a Carnot cycle 0.75, and the cycle, if the cycle direction is reversed, then what will be the COP of the Carnot refrigerator? Okay, so we know that heat engine works like this. This is a higher temperature source or a thermal reservoir, and this is a lower temperature thermal reservoir, and this is a heat engine. They are saying that this is going to be a Carnot heat engine. Okay, let Q1 amount of heat is taking from TH or higher temperature, and Q2 amount of heat it is rejecting to the lower temperature source, then W amount of work it is going to give. Okay, now we know that W is equals to what? Q1 minus Q2. Okay, and they have given the efficiency as, efficiency is given as 0.75. Efficiency is given as 0.75. Now let us analyze what is going to be the efficiency. So efficiency, we know that W, whatever the work we are getting divided by whatever the heat input we are going to give. So this is 0.75 and W is going to be your Q1 minus Q2 divided by Q1. So from here you can easily say that Q2 is going to be used 0.25 of Q1. Okay, if you do the calculation you will get that Q2 is going to be 0.25 of Q1. Okay, now this is the condition given. Now they have said that if the cycle direction is reversed, then what is going to be your COP of the Carnot refrigeration. Cycle direction is reversed means what? Now we need to turn this engine into a refrigerator, and for refrigeration what we need to give heat to the engine. Okay, and this Q1 direction will be in this way and this Q2 direction will be in this way. Okay, this is going to be a Carnot refrigeration. Just we are reversing the cycle and it is turning out to be like this. Okay, now from this what we know what is the relation between Q2 and Q1. Okay, since we are just reversing this, the values are not going to get changed. Okay, now we need to find what is going to be the COP of the refrigeration. And as we all know, for COP what we need the desired effect. That is whatever the temperature it is going to take out from the lower temperature so that it can maintain that temperature. Okay, so what is going to be the desired effect? The desired effect is going to be Q2. For refrigeration, desired effect is Q2. For heat pump, the desired effect is Q1. Okay, so this is going to be Q2. And what is the amount of energy you are giving as input? This is the W. W amount of heat you are going to give as input. So W is equal to what? Q1 minus Q2. Okay, now you know the Q2 relation. We need to take, we need to convert any one of these terms into the other one. Okay, either you turn Q2 into Q1, or you write Q2 in terms of Q1, or you can write Q1 in terms of Q2. Since we have direct relation of Q2 equals to 0.25 of Q1, I am writing Q2 in terms of Q1. So this is going to be 0.25 of Q1 divided by Q1 minus 0.25 of Q1. Okay, now from this if you subtract Q1 minus 0.25 of Q1, you are going to get 0.75 of Q1, and here you can take 0.25 of Q1. So Q1 gets cancelled. The remaining is 0.25 by 0.75. So ultimately your COP is going to be 0.33. Okay, so this is done. This type of question are very important for gate point of view. Okay, now what we can say, that if any conversion from engine to refrigeration question are given, then you can do it like this way and easily you can find out the answers. Okay.